uh, non-tunnel tunneling process and adiabatic time evolution in this system. The original motivation of these two works are not reproduced like this, but I'm providing you some more transparent motivations such that you will understand this more easily. So it starts from this Lindbergh quantum array setup. So this is given by the programmable Lindbergh quantum array in Harvard, the Xiao Wang group. So we have this type of setup given by this RB and 87 nuclear atom. So you can make up some ground state and the Lindbergh state, such as this. That you can build up a series of Lindbergh atoms put on this array, and you will have some effective Hamiltonian given by this Lindbergh quantum array. You find that there will be some detuning process between the ground state and the Lindbergh state, and also there will be some number counting operators of the Lindbergh state in the Hamiltonian, and finally there will be some interactions between the different two Lindbergh atoms. So if you make up a correspondence between the Lindbergh state with the sigma z operator, then you can transform this Hamiltonian into an antiferromagnetic Ising chain, and you will find that this part provides you some effective Ising spin, antiferromagnetic Ising coupling, and this will give you some non-trivial field. And this part will be transformed into some cosine sigma x minus sine sigma y. So this provides you some rotating transverse field. This model is antiferromagnetic with a rotating transverse field. So genetically, you can think about the transverse field is rotating in the x-y plane, but there will be some z components in the along the additional components along the z direction. So to make up both the rotating frequency and the longitudinal field HD, we are approaching to zero. So this is a very slow rotating process with a very slow zero, which is just a critical transverse field Ising chain with a very small longitudinal field. I've already introduced this in the morning. This corresponds to the low energy physics of this lattice model correspond to an integral quantum field. We can use a unitary transformation. If we apply this unitary transformation to the Schrodinger equation of this time-dependent Hamiltonian, you will find that this could be applied to cancel this time-dependent part of the Hamiltonian. And finally, you can directly the initial state with the additional unitary transformation given by this one. And the effective Hamiltonian turns out to be modified by minus omega 0 over 2j. So this is the time evolution process of this lattice Hamiltonian. This correlation is exact. And once the HD is not equal to omega 0 over 2, then this is another effective Elliott Hamiltonian. And if HD is equal to the omega 0 over 2, then this is just a critical transverse field Ising chain. So we can consider about the time I will make this rotating transverse field in the xy plane. So there will be a competition between the initial gap and the rotating frequency omega 0. So you will think about if the ground state, if the time dependent, if the ground state will be able to tunneling to the higher excited energy state, then if the time evolution is adiabatically time evolved, or it is there will be some many other tunneling process happening in the system. So to study this question, we can introduce and reduce the parameter kappa. This kappa is given by hz over omega 0 over 2. So if kappa equals to 1, it means that you have a gapless effective Hamiltonian. So here I just reminded you some information about the quantum EL integral model. So the quantum EL integral model is given by the general field perturbation to the critical Ising chain. You have 8 different types of quantum particles inside this model, and as I introduced in the morning, you can calculate the matrix element using the 4-vector bootstrap and so on. And things, and this is just a reminder to you. And then before we study the Tunnel tunneling process, we first consider a simple case of the initial model. That is, we consider the longitudinal field Hz is given by 0. So now we don't have the initial longitudinal field, and this is just a state is the ground state of the critical transverse field Ising chain, and the time evolution process gives here remains the same. However, now the time evolution process becomes that I have the H effective, which is the lower digit sector, is a quantum yield integral model, quench to the initial state. The initial state in the lower digit sector is a ground state of the central charge one-half conformal field theory. With this additional unitary transverse, this is sigma I alpha t. And I can first use the Schrodinger picture. The Schrodinger picture provides that the expectation value is given by the time evolved wave function is given by the summation of this sigma operator, and put the H effective to the initial wave function, such that this is a combination of the Heisenberg picture and the Schrodinger picture. So I can introduce a matrix element. This matrix element is known as d alpha. And you find that this unitary transformation applied to this sigma is just a given. Since this unitary transformation is a sigma z component. So this is just the equivalent to that I rotate the spin operator along the z direction. So under this scenario, you find that the sigma x part is given by the cosine omega t times this dx matrix element plus sine omega t times this dy matrix element. And the my part is given by cosine omega t times dy minus sine omega t times dx. And since sigma z is commutative with this unitary transformation, so mz is directly given by the two complete bases of the ES integral model, such that I can introduce this ANM matrix element, whereas before this matrix element, and therefore with the overlap between the quantum ES eigenbasis to the initial wave function, together with the matrix element. And you remember that the matrix element is just the form factor, so I can calculate this form factor. So then it seems that of this model. However, there will be several two questions here. So the first question is that we do not know how to compute the matrix element of the dy components, since we do not have the form factor of sigma y. But this can be dealt with a similar method, the commutation relation between the Hamiltonian to the sigma z operator. And the HES, there is a sigma x inside this Hamiltonian. So the sigma x commute with the sigma z will give you a sigma y. So we can directly extract out the sigma y component from the time derivation of the sigma z component. So this is how we can calculate the sigma y part. And the initial wave function, where I remind you that the initial wave function is given by the central charge one-half conformal field theory. The ground state of the central expand the initial wave function in the basis of the quantum ES integral model. How can we do this? Plus this perturbation. This perturbation is a relevant field perturbation. So here I just slightly modify this formalism. That is, I write down the central charge one-half conformal field theory as the perturbation of the quantum ES integral model, such that I can use the ES basis to represent. This seems to be a little bit complex, but this is just the direct application of the perturbation theory. So you just write down the wave function corrections of the in the basis of the quantum ES integral model. You directly in the second part of this perturbation result, there will be a delta zero. So this delta zero will give you some divergence in the second part. And in the first part, I insert two different complete bases in the matrix element. So if this two different complete bases becomes the same, then this will also contribute some delta zero in the first part. So somehow the perturbative framework. So I have to do some regularization to cancel these two infinities. How can we do this? So I will introduce you the so-called finite framework of the integral field theory. So typically we consider some quantum field theory. We are putting the corresponding quantum field theory in a infinite large systems. But now let's think about we put the quantum field theory on some finite system. So there will be a finiteness L for the whole system corresponding to quantum field theory. At the time is starting from the minus infinity to the plus infinity. So this is the structure of a cylinder for this geometry, for this geometry of this framework. So if we put the quantum field theory on this, the wave function will keep the same. So you will have something like e to the IPL equals to 1. This is a typical periodic boundary condition. If you have multi-particles, just like if the particle itself is a fermion, That depends on the numbers of the formula. You will have something like e to the IPL equals space. But here we're considering some integrable quantum field theory with the particles, which is generated by the Faraday small circle. Then this particle will exchange with every other particles inside this circle. And every exchange, it will give you a phase factor. This phase factor is contributed by the S matrix. So you will have this equation. It's modified periodic boundary condition. This is actually the same spirit of Bedondas, of coordinate Bedondas. So if you have some experience on that, you know that you write down coordinate Bedondas to this formula, type out of this formula. So you have the momentum of the corresponding will be modified by the logarithmic of the phase factor of the S matrix. And this will further provide you some relations between the infinite size system matrix elements with the finite size system matrix elements. Typically, you have some non-normalizable sets in the infinite set, but now in the finite set, we can normalize the quantum set with some dual delta functions. And more importantly, we can rewrite the form factors by using the exchange property. So you notice that corresponding particle state. But now we can rewrite it by using this exchange left-hand side to the particles in the right-hand side. And this will contribute to you some delta functions. And once if the two particles are the same, then this will contribute some additional delta zero. And this happens most strongly when the matrix element is diagonal. So the diagonal matrix element expansion process to this diagonal matrix element, which is given by a summation from the vacuum expectation value to the higher order particle contribution. For expansion, you will know that the previous introduced divergence. This divergence is vacuum. This divergence is exactly contributed by the vacuum part. So using this formalism, you can rewrite this part will exactly cancel with each other in the second order wave function corrections. Such that you will obtain a correct perturbative framework during this process. We can compare the results of the perturbative framework with some other types of numerical method, such as the compare with the truncated method quite well. However, for the high energy state, this will deviate away from the truncated method. But they will also do a numerical simulation given by the infinite time evolving block deformation algorithm. So for the lattice model, we can simulate the system with two periodic tensor structure, where we have choose where during the time evolution process, we have choose the truncated dimension of the system being a static value and a very long time evolution with the first order total security quantization. So the reason that treat the truncated dimension as a constant is because of that we only can you find that they due to the growth of the entanglement entropy, the truncated dimension should go as much as constant truncated dimension. The numerical result, so the right hand side value is a numerical result, can be compared with the Z operator. And this time evolution, this oscillations of the magnetization will not decay according to time. So this is some non-normalization structures during the time evolution process, which is due to the emergent integrability in the low energy sectors.
So that's still a slight difference that comes from the
yeah, so the slight difference comes from 2 points, and also the truncated of the bound dimension. Yeah. So this part of aerospace to cause this difference. And the second state result. However, for a lattice model, I start from a critical state. So there will be a relaxation process. The relaxation process, yeah, which cannot be found in the sphere theory result.
You can confuse them oscillation. The signal lines are
-1, so component like this. So they are contributed by 2 single particle mass difference. And another type of singularity is given by the edge singularity. So maybe you still remember that in the dynamics of the quantum EM particles, we have the van Hove singularity. So here, there's also contributions given by the van Hove singularity. And these 2 parts is given by the van Hove singularity. There's an additional edge singularity given by this logarithmic one. Hence, the delta function peaks, but you cannot observe it. For the XY component, this is directly given by the deformation of the cinematic component with the corresponding rotating frequency. So we can see this result. So the above one is a mathematical result. The below one is the numerical simulation. So you can see that there will be some peaks. This pink peaks is given by the single particle excitations, and there will be also some continued contributions in the emergence. In the analytics, I did not calculate all the components since the calculation of the form factor is very difficult. This omega 0. This can also be seen from the numericals. This peak is relatively small, but indeed it exists. So you have two different groups of the ES particles. And also this is for the one component. So you have the similar result. We can actually propose again the effective Hamiltonian. So this is more relevant to the Lindbergh quantum array. So I add some next nearest. So you will find the new critical point of this rotating transverse field Ising and do the simulation to the three components. You will find exactly the same result as the previous one. So this only depends on the universality class, but it's not influenced by the microscopic details of the corresponding model. So this is the magnetic oscillations in the Lindbergh quantum area in the rotating transverse field Ising. And the other one is about the barrier connection matrix element for the integral quantum field theory. So the starting point is again now we consider this model with additional longitudinal field. So now I set the longitudinal field being non-zero too. So I can consider if there's any possible adiabatic time evolution during this process due to the competition between the initial longitudinal field and the rotating frequency omega 0. So if we were to consider some adiabatic time evolution, this is equivalent to consider that we start from the initial eigenstate of some approximately peak in the corresponding instantaneous eigenstate of the time-dependent Hamiltonian. This is the definition of the adiabatic time evolution. And we can define two different types of quantum orbit. So the first one is known as the adiabatic orbit, which is just the instantaneous eigenstate of the corresponding Hamiltonian. The second one is known as the dynamic orbit. We can define some U1 invariant adiabatic orbit. So you satisfy this condition. It is equivalent to say that Cn, the absolute value of Cn, is larger than 1 minus delta. Consider a very simple two-level quantum system. So given by the constant part time derivative part together with this quantum matrix element. And we can define two adiabatic orbits, time-dependent orbit. So if you do this calculation, you'll find that you can calculate the quantum joyful potential. So you calculate the Tanoni probability of this two-level system. You find that it is given by the exponential to this part, to this family. It's exactly a very good test to check the result, which is directly given by the form factor of the corresponding local density field. And this will further provide you the result of this Jacobi. So the diagonal matrix, the matrix element, the barrier connection matrix element. So we conclude that the quantum field theory setup, you will have an initial quantum field theory, and you will have an initial quantum field theory, and you involve the system with some emergent quantum field theory in the world of quantum involve the system with some emergent quantum field theory in the world of quantum field theory. Then in this setup, if the effective adiabatic Hamiltonian falls in this form, which is given by the integration of the local density field, then the small diameter limit of the corresponding barrier connection matrix element proved in some lattice model. So you can consider about the transverse field Ising, and if you calculate the barrier connection matrix element, you will find that this is also given by. And based on this result, we can calculate the effective energy gap of the original model. So let me remind you, this model is so actually this talk there's too many components in this talk, but nevertheless orbit the exact time evolution process of this wave function given by the effective Hamiltonian quench to the initial wave function together with this unitary transformation, and we can consider the barrier connection matrix element and also the adiabatic time evolution in this system, such that we need to calculate the effective energy gap of this system. So if you calculate this, you find that the effective energy gap. So first of all, the quantum geometric potential given by two instantaneous eigenstates that contain capital N and capital M EL particles is directly given by the difference of these two form functions divided with their corresponding energy, with their corresponding particle energies. And this can be further reduced into this form, which is only related with the kappa and also the using the appendix of a paper. Now I just show you the results here. And the result could be compared with some numerical algorithm, just like the transverse converse approach. You find that the result matched with the numerical algorithm polynomial, which proves that our result is correct, that the contributions of the barrier connection matrix element is only up to two particle process. It's a tennis eigenstate that contain N and M particles. So the effective energy gap is directly readable given by these two parts. So this is the eigenstate, is the tennis eigenstate as a vacuum, as the other one as the single particle state. You will find that where this point is given by kappa equals to 8/50. So this 8/50 is somehow a typical scaling exponent for the quantum yield in one model. And this is independent of particle type during this process. You can also consider that you will find that if you calculate this zeros of effective energy gap, the zero momentum state for the two EL particle continuum will give you the kappa equals to 8/50. And the finite momentum state will contribute to some smaller effective energy gap. But if we consider any two different multi-EL particle state, then this but however, such a state, the density of such state for multi-particle state with a large upper bound is small, so you can nearly ignore all the contributions for this multi-particle state during this process. And the point, so as I said just now, the effective energy gap is used to characterize if there will be adiabatic time evolution happening. The kappa equals to 8/50 exactly serves as the upper bound for the transition between the time evolution process. So the variable we choose is the Loschmidt echo. So we can calculate the Loschmidt echo of the time evolving wave functions to the instantaneous eigenstate, to the instantaneous ground state of the time dimension will cancel with each other, such that the Loschmidt echo is directly given by this part. So in this case, we can introduce the so-called Loschmidt echo spectral entropy to count this strength of the many some logarithmic to the exponential, which gives you some linear behavior. So if you have a very strong many-body tunneling process, then this Loschmidt echo spectral entropy will have some linear dependence crossing behavior according to the system size. So this result has this Hamiltonian with the Randolph Fermi's components, and this is the energy of the corresponding state. And the famous one is given by two different sectors, the Randolph sector and the Lambert Randolph sector. This corresponds to the even number formed in this paper, the Egolf and the service paper in 21.1, omega 0/2. Let's say if actually is smaller than omega 0/2, corresponding to that kappa is smaller than 1, then the eigenstate of this effective Hamiltonian will also have a polarization direction. But this polarization is along the up direction and the down direction. So the effective Hamiltonian has a low sector in the down direction space. However, during this time evolution process, and this is why the quantum field theory cannot be used here. This is also why the quantum field theory cannot be used here. So the kappa equals 1 is an exact critical threshold. Is an exact critical threshold. We can then calculate the Loschmidt echo spectral entropy. So this is the result. You will find that when kappa is much larger than 1, this Loschmidt echo spectral entropy is approaching to 0, which just reflects that the state stays in the ground state. However, when kappa is smaller than 1, you will find that there will be some continuous growth of the where this kappa scaling behavior is given by kappa minus 1 and to the 50 power times L times the system size. And exactly on this kappa equals to 1 point. Okay. exactly this kappa equal to 1 point. You find that this dosimeter echo spectral entropy is linearly grows according to the symptom size, which is just the prediction I said just now, I explained just now. And for the kappa smaller one, and especially around this kappa equals to n over 15, you have a multi-new dimensional behaviors. However, this calculation is limited by our computational power. So even with this targeted method, we cannot calculate.
Remember what kappa is really I lost.
Okay, so kappa is just okay, so it's quite long before. Yeah. The kappa is h3 over omega 0 over 2. So you see the effective Hamilton that
the kappa essentially is hg. Omega 0 is actually a constant. It's a frequency of the driven.
Yeah, the frequency of the
the ratio is kappa.
Yeah, the ratio is kappa. So when kappa equals to 1, this is the kappa. And yeah, you will see some spin line. And you will also see some critical behaviors of the Nonequilibrium.
It's exponent of kappa, like in the horizontal axis.
Yes, yes.
Minus 1. Any understanding why this?
So the kappa scattering behavior, we do not have any analytical explanation.
This is also a numerical observation.
Yeah, this is numerical.
Then how do you know you should put this number in there? So just try.
Yeah,
we will just find this number is.
Yes, yes.
Okay. Later on, so kappa itself could also be this exponent. Right?
Yes. So this is going by a little bit previous relation. So as I said, so the notion and the many-body for the transition between the diagonal kappa evolution and the nano-general process, right? We can calculate. I said one of this state being the ground state, the other one being the single EM particle state. And if you do this calculation, you find that the zeros of the effective energy gap is given by kappa equals to n over 15, where it does not depend on the specific type of the particles. Effectively, I have the ground state here, the single particle state here, and once the kappa is smaller, the effectivity is similar to be I solve the position of this two states. So the ground state now is effectively higher energy than the is a basic understanding of the kappa equals to n over 15. It's just the ratio, the effective the zeros of the effective energy gap for the single particles. Yeah, single particles. And exactly at this point, you have this linear growth. So this understanding I also said about it. So since you consider this multi of this yeah. And for kappa around this n over 15, you have multi-new divergent behavior. However, limited by the computational power, we cannot really do further predictions with larger system size. So this is limited by our ability of the computation. But somehow we can still see that there will be multi-new divergent behaviors around this point. So this is suggests that the enhancement of the many-body models and then the end of this talk, so I give you some summary. So the quantum EM physics emerges from the Newtonian critical transverse field in chain. And the analytical time evolution could be characterized by the effective energy gap, where it contributed from quantum duration potential. So this is some take-home message. And yeah, and also specifically, Mr. Xiao Wang calculated a lot of data using the targeted method to do this have some calculation. And thank you very much.
你翻过去，你就把 kappa 或者这个 b， 然后把这个 g
你其实不用想诺什密特补偿
啊，补偿对，有点概述。
对，其实这很简单，这个实际上其实这样的，就是我现在可以算这个诺什密特 echo， 对不对？我可以插进去一组条卫星。其实就是我把那个
那个普世讲话的，把所有它
对，把所有它给它 overlap，
但这个只有一定是可以受这样做的，或者说有解析有些
对，是的。
不过数值上这个其实不太好，因为我要把那边他们要所有比
较糙，
对，但如果有个什么时间你也可以看看。
是的，
哎，我觉得这个好像我没有想过。
这可以证，的话可以去考虑一下这个 Q 随着这个，然后这个 DK 这个时间发现它是一样的。好，
我可能刚才有点乱说，就是你这里面那个1.8的那些 particle 对这个东西的影响是啥来着？
这个一般的 Python 是给了一个 description， 就是三号是这样，就是说这个模型里面呢，我们想要去算它10万的 gap，
这个在一般的框架下做这个计算。
对，我在一般的框架下做一个计算，这样的，对。
但是这些东西最后也能反映出一把的 party。
这个很困难，这个很困难
啊，这并不能。
对，因为这个模型其实我刚才其实漏讲了一点，这个模型有一个很有意思的地方，就是它的谱是不变的，就是这个 initial 的 model， 这个 model 是非常有意思，就是它的这个模型就是如果你量很少，对它的每个视差的等级都是一样
log 上面会降，对吧
？OK，
通常都在实际上低的地方，比如说10个负8，10个负7，在这个栏，就是说它的 overlap 它都在这个栏。你测的其实不是真正的 overlap， 是模式情况，对吧？那这就很难。你想，如果真的
有些人也是这样的吧？你好多值
对，
如果测 echo 本身也，但测的是 spectrum 能测吧？spectrum 的不能，实际上都是一变换。
对 sigma z 就你可以去拍那个照，就是两个关键函数，或者是单个的这个 sigma z 期望值，你说不定也可以看到一些迹象。
啊，对，这个地方是对我那个例子来说肯定可以
做这个计算。对，我觉得 out of time correlator 可能是一个
OTOC 你觉得？
对，告诉我的。但是你要取一些非常合适的 initial state，你那样取一个 tolerant，